Hi, my name is Kosta. I'm one of the designers working on Bifrost, focusing primarily on the simulation graphs and workflows. In the previous video, we covered the basic Aero graph template, what each node does, why they're wired that way, what the thinking behind it was, and how to build up to it. So if you haven't seen that video yet, please do go back and check it out. What we'll do now is take a look at some examples of graphs through the Bifrost browser so that we can see how the basic Aero graph template was tuned and what was added to achieve a particular effect and what the key characteristics of that effect are. The first example graph that we'll look at is the billowy smoke plume. So I'll just click on it and import it into my scene. And we'll see that the graph is automatically created for us and added to the scene. And so now if I look here, I have both the basic Aero graph template and the billowy smoke plume, and so we can compare to see what has changed between the two graphs. Okay, so the first nodes we'll take a look at is this group here that happens after the simulate Aero. That means that these nodes are not directly affecting the simulation since they come after this compound here. And so the first one we have here is simply a file cache node, and this will allow you to cache your simulation data to disk. Once you're ready to do that, you just change the mode from pass-through to something else. You set the file directory and all that stuff, and then this simply writes to disk. The second node that exists here is the assign material node. Now this is very cool because it allows you to bring in a material that exists in your scene. So bring that material into the board and then assign it to the object that you're creating in your graph, in this case Aero volume. And now I'll just give you a quick example of how this works. So if we look at the material editor here in Maya, the Hypershade, and we look at the Arnold section here, let's say I know I want to create a volume shader for my simulation, and I just click on this here to create the volume. And now if I bring back my graph and I go back to this other graph I've been using here as an example, what I could do now is simply just drag in my AI standard volume. So just middle click and drag that. And then I search for material here. So we have a node called assign material, and I know I want this to be the volume material since an Aero simulation is obviously a volume, so I just connect that here and then connect the output of the Aero simulation as a geometry. And so what this does is that it allows you to tweak the look of your volume here. And so if I go back to my billowy smoke example, this already comes equipped with an assign material node and a volume shader that has already been set up. And when you import the graph into your scene, it also imports that material. And so when you click on that here, if I click on my billowy smoke plume, I see that I have a material here that's been referenced. And this is an AI standard volume that has the correct channel names for the Bifrost data and so on and so forth. And so if I want to change the look of this, maybe I want to decrease the density, or maybe I want to change the color, I want to play with the transparency, so on and so forth. Everything is there already and it's already set up. Okay, so now that we've looked at these post-simulation nodes, let's take a look at what else we have. So if we go back and compare with the basic Aero graph template, we notice that there's two groups of nodes that were not there before. So the first ones are these here. So we have two nodes that are placed in between my emission geometry and my source air. And then if we look down here, we have a whole bunch of nodes that are being plugged into the influences port for the simulate Aero. And so let's first take a look at these two here. So when you're setting up your simulation, the first thing you want to ask yourself is, what do I want it to do? What does a billowy smoke plume look like? And so some things that might come to mind is that, you have a certain speed in mind with which you want the smoke to rise. Do you want it to rise really fast and then kind of slow down later? Do you want it to rise really slowly? All that stuff. So the first thing you want to set up is the temperature, and you also may or may not want to use some initial speed. And then obviously the other most crucial property that you want to tweak is the fog density. Do you want it to be, very thin smoke? Do you want it to be very thick? So on and so forth. And then you also know that you want to have more details, because this is a billowy smoke plume, it's not a smooth smoke plume. So you want some kind of fluffy details in the rise of the smoke. And so first things first, we're saying this is a billowy smoke plume. We want it to be fluffy, we want it to have a lot of details. And so the first thing you're going to do is set the style on the solve to fluffy. Now, we covered this in the first video, so if you haven't seen that, please go back and check it out. And so you have the default would be smooth, and so we change it to fluffy, and that way we have a nice, it's going to give us a nice billowy movement to the rise of the plume. And another thing I know that I would like to add is a little bit of initial speed in the Y direction. Now, obviously, because we're going to set a temperature higher than the ambient temperature, the force of buoyancy will make the smoke rise. But if you look at chimneys, usually there's like some pressure with which it's exiting the chimney, and then later it'll rise a little bit more calmly. So in order for us to get that initial pop out of the chimney, we'll just set some initial speed along the Y direction. But when you're setting up the temperature, it would be really cool if you were able to vary the temperature across the simulation geometry. So what does that mean? So when I set a temperature here, so let's say I set my temperature at 600, then the entire sphere will be emitting, every voxel emitted by this sphere will be at a temperature of 600. But because we want to get a more dynamic and realistic look out of this simulation, it would be really cool if we can vary the temperature that's being initiated. And so this is what the vary nodes do. So if I do a tab search for vary, I have something called a vary source property. And this allows you to vary any of the properties that you're going to initiate on your source. And so the one that I have here is vary temperature. And so what I did is I just renamed it from vary source property to vary temperature, and then I specify the property that I want to vary. So in this case, again, it's temperature. And if I look here, I'm varying it from a minimum of 20. So that's 20 is the ambient temperature that we have set down here in our Aero Solver settings, which I spoke about in the previous video. And so I know that some of the smoke will actually not want to move at all because it's set at room temperature, and then I have a maximum of 1000. So that, and this is a random variation, and it's animated. So that means that Bifrost is going to look at each vertex that exists on the emitting geometry. In this case, it's a mesh sphere that I've created in the board itself. And it's going to assign random values between 20 and 1000 to each vertex for temperature. And it's going to use this internally as a vertex map. So when you start to simulate, rather than all of the smoke rising at a temperature of 600, let's say, it's going to instead have a variation of temperatures between 20 and 1000. And the result from this is that you get a much more dynamic kind of simulation, because the difference between the temperatures is going to create differences in speed with which the smoke rises due to buoyancy, and this is going to create some natural turbulence and create and the result is a much more interesting flow than if you had everything set. Now, one caveat about this workflow is that when you use a variation here, the value you have set here will no longer have an effect. And so this is something to be aware of, because now I can change this and nothing will happen because the temperature is actually being controlled by this vary node here. And now, similar to how temperature is varied at sourcing time, so is fog density. So again, rather than have a solid fog density value of 5 throughout my emitter, I actually have a variation between 0 and 3. And I also use the bias here. What's the bias? The bias means that the bias allows you to tell the variation whether or not you want more of the minimum or more of the maximum. So the neutral position would be 0. -1 means you'll have almost 100% of the minimum value, and 1 would mean that you have almost 100% of the maximum value. So at minus 0.5, it means I'm going to have 50% more values of fog that are approaching 0 than I have 3. This is what's kind of gonna like break up the density. And again, it's animated, so at each frame, the distribution of the randomization across your geometry or through your geometry varies and changes. And so that explains why we have these two nodes here, and it's also a crucial part of setting up a billowy smoke plume that's going to look more dynamic and more realistic. Okay, so now that we've looked at what these variation nodes do here, let's have a quick look at the influence fields. There's going to be another video by Duncan Brinsmade that gets into the influence fields with great detail, so I do urge you to check that out. So for that reason, I'm not going to go into great depth here about the influence fields, but since influence fields play a role in almost every single example that you'll find in the Bifrost browser, I do want to give a little bit of information about these as well. And so on the Simulate Aero node, there's a port here called Influences. And for anybody who's done any simulation work in the past, you're probably already aware that influence fields play a huge role. Now, in our case, for Bifrost, the influence fields are a tool that we've designed so that you can have artistic control over the physical accuracy of the solve, meaning that you don't actually need, they're not absolutely necessary to get an accurate physical looking solve, but the minute you want to start having artistic control over its behavior, this is where the influence fields come in. And so one influence field that is very common in most graphs is a dissipation influence. This just means that at some point the smoke that you're emitting will dissipate and disappear. And the reason why you want this is because otherwise you have to keep track of so many voxels over the course of the simulation, and it's just going to get heavier and heavier. So now for a chimney, obviously the smoke does dissipate, so you can decide how soon or how late you want it to dissipate. The way this node works is simply by calling the property which we want to dissipate. In this case, it's the voxel fog density, and then you could input a rate at which it will begin to dissipate. So smaller numbers here will make the fog dissipate slowly, and higher numbers will make it dissipate more fast. Having said that, the property here doesn't necessarily have to be density. You may want to dissipate temperature, for instance. So if you start with a very, very high temperature and you want to emulate the act of cooling, then you can dissipate the values for temperature as well using this dissipation influence. That's why it's not just called dissipate fog, and it's just a general dissipation influence. Another thing we have is vorticity. Now, why do we want vorticity? So as I mentioned earlier, we're using the fluffy mode in the solver settings to simulate the billowy smoke plume. However, depending on the artistic direction that you're aiming for, you may want even more detail than that. And so this is where the vorticity influence comes in. To put it simply, mathematically, what happens is that the curl of the velocity is computed for every voxel, and then that's reapplied to the flow. That's an oversimplification. For more information, you should probably look at Duncan's videos or do an internet search for vorticity confinement. But visually what happens is that you start to get some finer details in your flow. So where you had some macro details, like maybe some big bubbles, some big puffs, then you can start to get details inside of those puffs. And so you start getting more vorticity, more vortices forming, and the flow becomes a lot more energetic and dynamic. And so let's have a look at some examples. So first things first, this is what my simulation looks like without any vorticity at all. And now I just want to mention that everything I was talking about earlier with the variation on density and temperature, we could see it's happening here. Because it's animated, it actually changes at every frame, and it changes quite rapidly, so you can see it kind of flickering down here. But what this is doing is that it's creating all of these extra details and extra dynamics that we're getting due to the variations in speed caused by the varying temperature, and also we have some variation in the level of densities that make it look much more interesting. So now let's look at an example of what it looks like when we add vorticity. I'm just gonna remove this and I'll talk about that in just a minute. So we just saw what the simulation looked like without vorticity, and now this is what it would look like with vorticity. And so if I press play here, we see that we actually have a lot more detail. There's a lot finer action happening here. We also notice that after a while, it kind of starts to look bad. And this is because the vorticity is continuously calculated. And so everywhere where vorticity has been applied, it gets reapplied and reapplied and reapplied. And eventually, it just turns into this static here. And although it looks good for a while, like perhaps we love how it looks here, or maybe even here, you can see that we're starting to get some smaller details inside of the larger ones. It would be great if that could continue on forever without this staticky look emerging. And so that's where the modulation comes in. And so if we go back here, we had this modulate influence node. So let me explain to you what this does. So this node is telling the solver, okay, I want to apply vorticity, and so that happens. And then this node says, well, you know what? Actually, I want you to look at a property. In this case, we're going to look at voxel fog density. And I want to modulate the vorticity using the values of voxel fog density as they're being solved. And so what happens is that you're going to have the possibility of applying more vorticity where you have higher values of fog density, and less vorticity where you have lesser values of fog density. And so in the areas where the density is kind of breaking up and is thinner, you'll have less vorticity, and then as your flow starts to dissipate, because we do have a dissipation influence that's also active right now, and so as things start to dissipate, the vorticity will begin to lessen. And so all of these things combined would make it such that the vorticity never becomes so large in magnitude that we get that staticky look. And so you basically just have to chain it up to any existing field. And so you can modulate any field with any property. In this case, I'm using voxel fog density, but I could have used temperature. That way, if I had a variation of temperature, I can say, well, okay, give me more vorticity where temperature is higher and less vorticity where temperature is lower. And what's really cool is that if we go back and think about what we did at emission time, which is we're varying the temperature, we're varying the density. And so from the get-go, we know that we have uneven values of fog density. And so because we're modulating vorticity with fog density, which is already not homogeneous, we know that we're going to get a much cooler looking simulation because we're going to have varying degrees of vorticity. And so that's going to make it look a lot more realistic. And so the min and max values that exist on the modulated influence read something along the lines of, okay, so I have a vorticity influence, its magnitude is 1.5. And so what I'm saying here is that, okay, I'm looking at voxel fog density. And so any voxel that has a value of 0.25 for fog density will have 0 vorticity influence. And then any voxel that has a value of fog density of 2 will have the maximum vorticity. In this case, it's 1.5. So this is essentially a way of remapping the values of vorticity depending on the voxel fog density. And as I mentioned earlier, I'm sure Duncan goes into much more detail about that workflow in his fields videos. And so if we now have a look at what happens when we do that, so I'll just bring my video in here. If I press play now, we can see that I'm getting a lot of that cool detail I was getting earlier. But as the flow dissipates, the vorticity also lessens. So the net result is that we have a little bit best of both worlds. You know, we have the vorticity, we have the dissipation, we have vorticity only where density is high, and we have less vorticity where density is low, and as a result, it prevents the emergence of that staticky look. And so that's one really cool way of having the variations at sourcing time work together with influence fields in combination with modulation so that you can get some very cool looking results. And then similarly down here we have some wind, and it's also being modulated, in this case also with voxel fog density, but as I mentioned earlier, you can modulate with anything you like. And so if we want to have a look at what it looks like with the wind on, it looks something like this. And so what's happening here is that we're also modulating the wind with with density. So what that means is that areas of higher density will feel more wind and areas of lower density will feel less wind. This is why some of the smoke plume here is kind of being left behind while some of it moves to the right, which is the direction I had given to the wind. If I hadn't had the modulation on, then everything would be moving together to the right, depending obviously on the magnitude of your wind and the drag force and all of that. So that pretty much takes us through the billowy smoke plume graph preset, and just to recap, we have some variation on fog density and temperature at sourcing time, which causes a little bit of, which breaks up the homogeneity of the emission. We have the solver settings set to billowy, and we have some dissipation, vorticity, and wind influence fields which are modulated by the fog density. So now that we've learned a little bit more about the billowy smoke plume effect and graph, let's have a look at another example. This time I'd like to look at the smoke trail, so I'm just going to click on that and import it. Now if we think of a rocket in real life, a rocket is propelled forward by the backwards thrust of a combustion reaction, which is also what leaves the smoke trail. Now in Bifrost, although we can try to model this with a combustion system, we could actually get a very good approximation with only a standard Aero simulation. So that's why if we look at this graph here, we're not going to see any combustion nodes. And this is kind of similar setup as what we had with the billowy smoke plume. In other words, we have our source, we have a couple of variations here, not the same ones, but we'll talk about that. And we don't have as many influence fields. We just have one influence field here, and also the same setup for file caching and assigning a material. So let's just have a quick look at what this simulation looks like. So just looking at this, we notice at first glance that obviously the smoke is quite billowy and fluffy, and so that immediately means that in the graph here on the Aero Solver settings, we're using the fluffy style for the transport interpolation. But another one of the key characteristics of this simulation is this powerful backwards thrust, which is giving the sense of pushing the object along its path. So in order to get this backward thrust in Bifrost Aero graph, we have to take advantage of the inherent velocity property that exists on the source air. So if we take a look here, if we take a look at the source air, there's something called inherent velocity. And now what this usually does is when you have an animated mesh as your source, it'll look at the speed at which, it'll compute the speed at which the mesh is moving, and then it'll give you the control over how much of that velocity you want the emitted aero smoke to inherit. Now, by default, this is set to 1, which means that as an object moves along, the smoke kind of moves along with it. But if you want to get this backwards push type of effect, then you can use negative inherent velocity. So that means that as the object is moving forward, we are giving an equal but opposing direction to the velocity of the aero. And so as the object moves front, the smoke moves backwards. And this gives that illusion of thrust. Now, if we look here, we have another one of the very source nodes that we talked about earlier in the billowy smoke plume example, but this time we're using a variation on this inherent velocity. So we have the minimum set to -3 and the maximum set to 1. So that means that certain vertices on the emitting object are going to have an inherent velocity of -3, so those will be pushing the smoke back, but then some of them will also have a positive inherent velocity. And so this contradictory force of some of the smoke being sucked along with the moving emitter and then some of it being pushed backwards is going to create a natural turbulence in the airflow. And when you do that, it's going to create a nice spread as the simulation progresses. So we see here that the simulation is pushed out backwards, and then as time goes by, it starts to spread, and there's like a lot of details in here. And this is happening because of the variation in the inherent. So you can play along with that to achieve different effects. If you want a straighter, less spreading kind of trail, then you may not want as much variation in the inherent. So just to recap the key controls in the Bifrost smoke trail graph, which produce the key characteristics for this type of simulation. First things first, we have the fluffy style on the Aero Solver settings, And then very important, we have a variation on the inherit, which is in majority negative to get that pushback, and also a little bit of positive just to create some turbulence in the airflow, which produces some natural vortices. As you've noticed here, we only have a dissipation field. We don't have a vorticity field. One can be added for even more details, but because of the natural airflow and turbulence that's produced by varying the negative inherent velocity, it gives us some nice details and also a nice spread. And as it's specified here in the backdrop, if you reduce the negative inherit or reduce the variation, reduce the delta between the positive and negative, then you'll get a straighter trail. We have a little bit of variation on the fog density, and then over here we have the trail smoothness, which helps reduce any amount of stepping that may occur depending on the speed of your geometry. And I've also written here in the backdrop that at worst, if your geometry is moving so fast and your trail is moving even faster in the negative direction, then you might also have to increase the substeps of the solver itself. But as a first step, it's better to try the trail smoothness because it only applies to the specific source. And that's it for the smoke trail graph.